In plumbing design, accurate domestic water pipe sizing is essential to ensure reliable water delivery, maintain pressure, and prevent excessive noise or energy loss. The process involves determining how much water is needed for both hot and cold systems, and then selecting the right pipe size based on friction loss and velocity criteria. Let's walk through the step-by-step procedure used by engineers and designers in professional practice. The first step is to determine the flow requirements for both hot and cold water. Start by calculating the fixture unit counts. Using a flow calculation sheet shown in figure, locate columns C and D to find the total number of fixture units for the section of pipe being analyzed. Once you have those totals, use the Hunter's curve chart to convert fixture units into demand flow in gallons per minute. For large buildings, refer to figure 3.1. For smaller buildings, use figure 3.2. If the building uses flush valve toilets, use curve 1 for estimating cold water demand. If it uses flush tank toilets, use curve 2 for both hot and cold water calculations. This step gives you the estimated GPM for each section of your water distribution system. Next, we establish design limitations for the system. These limitations define how much pressure drop and velocity are acceptable within the piping network. Consult local plumbing codes and apply sound engineering judgment to set these parameters. Here are 3 common design approaches. Pressure drop limitation: limit total friction loss to 5 psi per 100 feet of pipe. Combine limitation: maintain the same 5 psi per 100 feet while keeping velocity below 8 feet per second. Velocity-only limitation: restrict water speed to between 6 and 10 feet per second, depending on the pipe material and noise tolerance. These limits help maintain steady flow, prevent pipe erosion, and minimize pressure fluctuations at fixtures. With the fixture units and design criteria established, the next step is to select the pipe size. Choose the appropriate chart based on pipe material and internal roughness. For example, figure 3.3 for copper tubing, figure 3.4 for fairly smooth pipe, and figure 3.6 for rough pipe. Now, locate your calculated fixture unit count on the horizontal axis. Then, trace vertically upward until you intersect the chosen design limitation, such as the 5 psi per 100 foot friction loss line or your maximum velocity line. From that intersection, trace horizontally to determine the required pipe size. If you're applying a simple 5 psi per 100 foot limit without worrying about velocity, you can use the simplified tables, figure 3.7 for copper or figure 3.8 for rough pipe, to quickly find the correct pipe diameter based on fixture unit range. The sizing of the street supply pipe is a special case. It's handled differently from interior distribution piping. Here, you'll calculate total fixture units using column A of figure 1.1. Add 75% of the cold water fixture units and 75% of the hot water fixture units for each fixture that requires both. This adjustment accounts for diversity, since not all fixtures operate at once. Then, use the appropriate sizing chart, such as figure 3.3 for copper pipe, to select your street supply size. It's acceptable to exceed the 5 psi per 100 foot rule for this section because the run is typically short and located outdoors, where higher velocity, noise isn't a concern. To summarize, determine fixture unit counts and convert them to GPM using Hunter's curves. Set design limitations for friction loss and velocity. Use the appropriate sizing charts to select the correct pipe diameter. By following this method, you'll ensure your domestic water system delivers the right flow, maintains pressure, and operates quietly and efficiently. Thanks for watching. Keep learning and keep designing systems that perform perfectly from the first drop to the last.